Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
All right, let's just get straight into it. I want you to picture something. Picture the Milky Way galaxy, not just as a band of light in the night sky, but that classic, top-down view, the beautiful spiral arms, the billions of stars.
The image we all have in our heads.
Exactly. And now, zoom in, go past our little solar system, past the Orion Arm, and head right for that bright, glowing bulge at the very center. And then keep zooming right to the absolute bullseye. For decades, we've had this very comfortable story about what's there.
We have. The story is Sagittarius A, the supermassive black hole.
The anchor, the cosmic behemoth that holds everything together. It's the standard model of galactic astronomy, right? It's been the bedrock.
It absolutely has. We're talking about something with a mass of 4 million suns, all crammed into a space that's, roughly the size of Mercury's orbit around our sun. It's the only thing that made sense.
Right. It's what won the Nobel Prize in Physics back in 2020. The work done by Reinhard Genzel and André Ghez was incredible. They tracked the stars whipping around that central point.
A violent dance, as it's often called.
A very violent dance. And they proved there was an unbelievably compact, massive object there. The conclusion just seemed inevitable. It had to be a black hole. Nothing else in our physics toolkit could possibly fit the math.
Until now.
Until February 5th, 2026. Just a few days ago, a new study gets published in the monthly notices of the Royal Astronomical Society.
Right, a prestigious journal.
Very. And this international team, they're looking at the exact same data, the same Nobel-winning observations, the same stars, the same gravitational effects. And they're essentially raising their hands and saying, hang on a second, we don't think that's a black hole.
Which is, that's a bold claim. To challenge the existence of Sagittarius A as a black hole is to poke at one of the most fundamental assumptions in modern astrophysics.
It's a huge deal. But this isn't some fringe idea. Their argument is really methodical, and it's built on a potential solution to an even bigger problem, the dark matter problem.
And that's what makes it so compelling. It's not just saying it's not A. It's proposing it's B, and B also explains C, D, and E.
That's the whole core of this analysis today. They aren't saying there's nothing there. They're not disputing the 4 million solar masses. What they're saying is that it's not a singularity. It's not a hole in the fabric of space-time.
Instead, it might be a gigantic, incredibly dense clump of dark matter, a core made of something called fermions.
And if they're right, and that's a huge if, but if they are, this changes basically everything. Our understanding of gravity, the way galaxies form and evolve, and, it could finally give us an identity for the invisible stuff that makes up something like 85% of all the matter in the universe.
It offers what physicists are always searching for, a unified framework, a more elegant explanation. Instead of a galaxy being this collection of disconnected part stars here, black hole there, dark matter halo somewhere else, this paper proposes that it's all two sides of the same coin.
A single, continuous substance that explains the chaotic, violent center and the gentle, vast edges of the galaxy. It's a really beautiful idea.
It is, but it has to stand up to the evidence.
Right. So that's what we need to unpack. We need to start with the reigning champion, the incumbent, the black hole theory. We need to really understand why it's been so successful and why it's so hard to challenge.
So then we meet the challenger, this fermionic dark matter core. What is it and how does it work?
Exactly. And then we have to weigh the evidence. We'll look at the stars in the middle, the so-called S stars and G sources, and then we'll look at the data from the very rim of the galaxy from the Gaia mission.
And we absolutely cannot forget the elephant in the room, or I guess the shadow in the room.
The picture, the Event Horizon Telescope image.
Yes. We have a photo that supposedly shows the shadow of a black hole. How do you explain that picture if there's no black hole to cast a shadow? That's a very tall order.
It is. We will get there. But let's start with the status quo, the incumbent. Why were we, and why are most astronomers still so convinced that Sagittarius A is a black hole? It all comes down to those S stars.
The S cluster, yes. This is a group of surprisingly young, very bright stars that live the absolute most central part of our galaxy, the innermost parsec, which is about 3 light years across.
So this is extreme real estate.
The most extreme. And the most famous of these stars is one called S2. We're tracking dozens of them now, but S2 was one of the first, and it's our best studied example. These stars are, for all intents and purposes, are test particles. We can't see the central object itself because it doesn't emit light.
It's dark.
It's dark. But we can watch how these bright stars move in response to its gravity, and that tells us everything we need to know.
And their movement is, to put it mildly, extreme.
It's violent. S2, for instance, is on this long, stretched-out elliptical orbit. It takes about 16 years to go around once, but at its closest approach, a point we call the periapse, it gets incredibly close to the central object.
And it speeds up, right, like a comet whipping around the sun.
Exactly like that, but on a scale that's hard to comprehend. To put it in perspective, the Earth orbits the sun at about 30 kilometers per second. That's fast for us.
Pretty quick.
S2, at its closest approach, has been clocked at speeds exceeding 7,600 kilometers per second.
7,000?
Yes. That's about 2.5% of the speed of light.
That's just staggering. And to keep a star, an object that massive, from just flying off into space when it's moving that fast, the gravitational pull has to be, I can't even imagine.
It has to be immense. And this is the beauty of orbital mechanics. By precisely measuring the shape and the period of that orbit, you can use Kepler's laws and Newton's laws, well, actually Einstein, since we see general relativistic effects, to calculate the mass of the object it's orbiting.
And that's where the number comes from.
That's where the 4 million solar masses figure comes from. The orbits of S2 and the other S stars demand that much mass be sitting right there in the middle.
Okay, but mass alone isn't proof of a black hole, is it? I mean, couldn't it be something else? Like, what if it's a really, really dense cluster of old, dead stars, like neutron stars or stellar mass black holes?
That's a great question, and it's the first thing astronomers tried to rule out. So you could, in theory, get 4 million solar masses from a cluster of other objects. The problem is size, the constraint of space.
How close S2 gets without crashing into anything.
Exactly. The periapse of S2's orbit tells us that all of that mass has to be contained within a sphere with a radius of only about 120 times the distance from the Earth to the Sun.
So 120 astronomical units, that sounds big, but for 4 million suns.
It's impossibly small. If you tried to pack, say, 4 million neutron stars into that volume of space, they would be so close together that their orbits would become unstable in, well, less than 1 million years. They'd either fling each other out, or more likely they'd merge and rapidly collapse into a single supermassive black hole anyway.
So you'd end up with a black hole one way or another.
You would. The same logic applies to any other conceivable collection of objects. A gas cloud would be blown away or would have already formed stars. A cluster of regular stars would be far too big. You run through the list of known astrophysical objects.
It's a process of elimination.
It's a process of elimination. And after you've eliminated every other possibility within the standard model of physics, the only thing left that can be that heavy and that small is a singularity.
A point of infinite density wrapped in an event horizon from which nothing can escape.
That has been the only working assumption that fits all the data. It perfectly explains the orbits we see.
Until this study comes along, the Challenger. The paper is titled Milky Way Center, a supermassive black hole or a dark matter core. The lead authors are Dr. Carlos Arguez and Valentina Crespi, part of a big international collaboration. And they're effectively adding a new suspect to that process of elimination lineup.
A candidate that wasn't on the books before.
The fermionic dark matter core. Okay, we need to be really careful with our terms here because dark matter is a loaded term. For most people, when you say dark matter, they think of one thing.
WIMPs. Weakly interacting massive particles.
Right. This has been the leading theory for, 30, 40 years? These big, heavy, slow-moving particles that just sort of drift around and provide all the extra gravity we need to hold galaxies together.
That is the cornerstone of the cold dark matter, or CDM, paradigm. The idea is that these WIMPs are maybe 100 times heavier than a proton. They move slowly. That's the cold part. And they barely interact with anything except through gravity.
But the big problem with WIMPs is we can't find them.
We can't. We have spent decades and billions of dollars building these incredibly sensitive detectors, deep underground, shielded from all cosmic rays, usually giant vats of liquid xenon or other materials, waiting for a WIMP to just bump into one of our nuclei.
And nothing. Not a single unambiguous detection.
Which doesn't mean they're not there,
Yeah.
but it has certainly opened the door for people to seriously consider alternative ideas.
Yeah.
And this new paper is built entirely on one of those alternatives. It's based on fermions.
Okay, so let's define that. A fermion is a category of particle, right? Like a boson is the other main category. What's the difference?
The fundamental difference is a quantum mechanical property related to their spin. But the consequence of that property is what really matters here. Fermions obey something called the Pauli exclusion principle.
I remember that from chemistry. It's why electrons in an atom have to stack up in different energy shells.
That's it exactly. The Pauli exclusion principle states that no two identical fermions can occupy the exact same quantum state at the exact same time. You can't put them in the same place with the same energy and the same spin. They are, in a sense, antisocial particles.
They need their personal space.
They absolutely do. Bosons, on the other hand, love to clump together. You can pile an infinite number of bosons, like photons of light, into the same state. That's how a laser works.
So fermions are territorial. What happens if you try to squeeze them into a small space anyway? Say, with gravity.
They push back. This is the crucial part of the theory. As you compress a gas of fermions, they start filling up all the available low-energy states. To squeeze them further, you have to force them into higher and higher energy states, which requires a tremendous amount of energy. This resistance, this pushback, is a real physical pressure. It's called degeneracy pressure.
And this is a known force in the universe. This isn't theoretical.
Oh, not at all. It's the force that supports white dwarf stars. A white dwarf is the remnant of a star like our sun. Gravity is trying to crush it into nothing, but the electrons inside, which are fermions, exert enough electron degeneracy pressure to hold it up and keep it stable for trillions of years.
Okay, so apply that same idea to dark matter. Our Wheels and his team are not talking about heavy WIMPs. They're talking about a very different kind of dark matter particle.
Yes, they're modeling it as a light neutral fermion, sometimes called a sterile neutrino or a darkino in the literature. The specific mass they use is around 50 kilo electron volts, or keV. For comparison, an electron is about 511 K. So these are very light particles.
And their theory is that the center of our galaxy isn't a hole. It's a giant stable ball of these light dark matter fermions.
Exactly. A huge collection of them, pulled together by their own gravity over billions of years. As gravity tries to crush this ball into a single point, into a singularity, the fermion degeneracy pressure pushes back.
And it creates a stalemate, a stable equilibrium.
The result is a stable, super dense core. It's not a singularity. It has no event horizon. It has a real physical size. But, and this is the absolute key to the whole argument, it is so compact, so massive, that from a distance, its gravitational field is indistinguishable from that of a black hole of the same mass.
So if you're the star S2 and you're making that high-speed turn, you don't know and you don't care if the object pulling on you is a point of infinite density or a ball of fermions. The pull feels exactly the same.
Precisely. The researchers did the math. They calculated the gravitational potential of this fermionic core. And they found that for any distance greater than about 2 or 3 times the Schwarzschild radius, the radius of the black hole's event horizon, the gravity is identical to what general relativity predicts for a black hole.
And the S stars, even S2 at its closest, are always further out than that.
They are. They orbit far enough out that they would never notice the difference.
So the Challenger, this dark matter core, it survives the first and most important test. It explains the S-star orbits just as well as the incumbent black hole theory.
It does. It matches the observations perfectly.
But the paper goes much further. It claims this model does something the standard black hole model can't do. It solves what they call the core halo problem. This brings us to this really elegant idea of a unified entity.
This, for me, is the most beautiful part of the entire proposal. To really appreciate why it's such a big deal, you have to understand just how, well, messy and disconnected the current model of a galaxy is.
Right. In the standard textbook view, we have all these separate ingredients that we just kind of stir together. First, you have the baryonic matter. That's us. That's stars, gas, planets, dust, all the normal stuff made of protons and neutrons.
The stuff we can see.
Then you put a supermassive black hole right in the middle, which is its own special kind of object, formed in a specific way.
And then, surrounding the entire visible galaxy like a giant invisible sphere, you pour in the dark matter halo, which is assumed to be made of a completely different substance, like WIMPs.
It's like building a car where the engine is made of iron, the chassis is made of carbon fiber, and the tires are made of cheese. They're all there, they interact, but they're fundamentally different things.
An excellent analogy. And in our cosmological simulations, we treat them as different things. The black hole is one type of particle in the simulation, the halo is another. They interact through gravity, but they have distinct origins and properties.
But this new model says no. It says the engine, the chassis, and the tires are all made of the same high-tech alloy. The entire galaxy, from the hyperdense core to the most diffuse outer fringe, is all made from the same sea of dark matter fermions.
This is what Dr. Arguelles highlights in his comments on the paper. He says, "We are proposing that the supermassive central object and the galaxy's dark matter halo are two manifestations of the same continuous substance."
A continuous distribution. How does that work? How can one substance form both a tiny, dense core and a giant, fluffy halo?
It's a natural consequence of how a self-gravitating gas of fermions behaves. The team solved the equations of general relativistic hydrostatic equilibrium, the Tolman-Oppenheimer-Volkoff equations, for a gas of these particles. What they found is that it naturally settles into a two-phase structure.
Two phases, like water and ice.
In a way. In the very center, where the gravitational pressure is at its absolute maximum, the fermions are forced into that quantum degenerate state we talked about. They become incredibly dense and compact, forming the core that mimics the black hole.
Okay, that's phase one, the dense core.
Then, as you move outwards from the center, the gravitational pressure drops. At a certain point, it's no longer strong enough to keep the fermions in that degenerate state. So there's a transition, and they start behaving more like a classical diffuse gas. And that diffuse gas forms a vast, extended halo.
So the monster in the middle isn't a separate creature that the galaxy captured. It's just the densest part of the galaxy itself.
It's the peak of the mountain. It's not a separate rock placed on top of the mountain. This unifies the physics in a profound way. You no longer need one theory to explain how the black hole formed and a totally separate theory to explain the dark matter halo. They form together as a single system.
That feels so much more natural. As the primordial cloud of dark matter collapsed in the early universe, this dense core would just condense out in the middle.
It would precipitate out, yes. And this has another major benefit. It helps solve a huge puzzle that's come from the James Webb Space Telescope recently.
Right, the impossible early black holes. JWST is seeing these enormous billion solar mass black holes at extremely high redshifts, meaning very, very early in cosmic history.
So early that there doesn't seem to have been enough time for a normal stellar mass black hole to grow that big by eating gas and stars. There's a physical speed limit to how fast a black hole can feed. It's called the Eddington limit. If you try to shove matter in too quickly, the radiation from the meal itself blows the rest of the food away.
It's a self-regulating process.
It is, and it makes it very difficult to explain how these giants got so big so fast. But a dark matter core doesn't need to eat. It forms directly from the gravitational collapse of the halo itself. It can be born big. This model naturally explains why we see these gigantic objects so early in the universe's timeline.
That's a very powerful theoretical argument in its favor. But let's bring it back to the Milky Way, back to the hard data. We've established that the dense core part of the model works for the S-stars in the center. But it's a unified model. If you're also changing the halo, that has to change how the rest of the galaxy spins.
It absolutely does. And this is where the European Space Agency's Gaia mission becomes the crucial second piece of evidence.
Gaia is just a revolutionary instrument. It doesn't take those breathtaking, colorful pictures like Hubble or Webb, but what it does is arguably more important for understanding our galaxy's structure. It's an astrometry machine.
It's a cosmic surveyor. Its job is to measure the precise position, distance, and motion of billions of stars in the Milky Way with unprecedented accuracy.
And from that data, we can build the most detailed map of our galaxy ever created, including its rotation curve.
A rotation curve is a simple but powerful tool. On the x-axis, you plot the distance of a star from the galactic center. On the y-axis, you plot how fast that star is orbiting.
And if our galaxy was just the stars and gas we can see, that curve should drop off as you go further out. And just like in our solar system, Mercury moves super fast, Neptune moves very slowly. That's Kepler's law.
Correct. The gravitational pull gets weaker with distance, so things should slow down. But for decades, we've known that's not what happens in galaxies. We see a flat rotation curve. The stars on the very edge are moving just as fast as stars much closer in.
Which is the primary piece of evidence for dark matter in the first place. There has to be a bunch of invisible mass out there in a giant halo whose gravity is keeping those outer stars moving so quickly.
Exactly. But the latest data from Gaia, Data Release 3, it extended that rotation curve further out and with more precision than ever before. And it saw something new, something a bit weird at the very, very edge.
The curve isn't flat forever.
It isn't. At the outermost observable limits of the Milky Way, the orbital speeds finally start to drop. We see a Keplerian decline.
So does that mean we're finally reaching the edge of the dark matter halo? We found the shoreline of the invisible ocean.
In a sense, yes.
Yeah.
We are seeing the gravitational potential finally begin to weaken. Now, here's the problem this poses for the standard cold dark matter model, the WIMP model. CDM halos are typically modeled with a specific density profile, most famously the Navarro-Frank-White or NFW profile. And this profile predicts a very large, very fluffy halo that just sort of trails off gradually into infinity. It has a power law tail that keeps going for a very long time.
So a standard WIMP halo would predict that the curve stays flat for much longer. It would struggle to explain why it drops off so relatively sharply.
It struggles, yes. You can make it fit, but you often have to sort of artificially truncate the halo in the models. You have to say, well, the halo just stops here. But the fermionic model from Arguelles' team, it predicts this decline naturally. It's a built-in feature of the model.
Why? What is it about these fermion particles that gives the halo a sharper edge?
It goes back to their quantum nature and the thermodynamics of the gas. Because the particles aren't cold, they have some small intrinsic velocity, and because of the phase space constraints imposed by the Pauli exclusion principle, the resulting halo structure is naturally more compact. It has a tighter, more defined boundary than a WIMP halo.
It's not as fluffy.
It's not as fluffy. And when the researchers took their unified model, the dense core plus the extended halo, all from one equation, and compared it to the Gaia rotation curve data, including the normal matter of the disk and bulge, it was a perfect fit.
It matched the Keplerian decline at the edge without any special tweaks.
A beautiful fit right out of the box.
Okay, let's just recap the evidence so far. The fermionic dark matter core model successfully explains the orbits of the S-stars at the center.
Check.
It provides a unified framework for the core and the halo, solving a major theoretical headache. Check.
Yeah.
It naturally explains the existence of supermassive objects in the very early universe, which JWST has been finding. Check.
A big check on that one.
And it perfectly fits the entire galactic rotation curve from Gaia, from the inner parts, all the way out to the Keplerian decline at the edge. Check.
Check. And it accomplishes all of this without needing a singularity, a point where our known laws of physics literally break down.
That's a pretty compelling case. But let's dig a little deeper into the central region. There are other strange objects there, not just the S-stars. There are the G sources.
Ah, yes, the G objects,
Right.
G1 and especially G2. These were discovered in the mid-2000s and early 2010s, and they've been a puzzle ever since.
What are they?
Well, that's a question. Spectroscopically, they look like giant clouds of gas and dust.
Yeah.
But dynamically, they move like stars. They're on these very tight, very eccentric orbits around the galactic center, just like the S-stars.
And G2 became famous because it was on a collision course, wasn't it? Or at least a very close flyby.
It was. Its orbit was predicted to take it right through the most intense gravitational region around Sagittarius A. And astronomers worldwide got their telescopes ready for a spectacular show.
What were they expecting to see?
If G2 was just a simple gas cloud, they expected it to be completely torn to shreds by the black hole's tidal forces, a process called spaghettification.
Right, where the side of the cloud closer to the black hole gets pulled so much harder than the far side that it just gets stretched out into a long noodle of gas.
Exactly. And they predicted that this noodle of gas would then get captured by the black hole, spiral in, and cause a massive flare-up as it was consumed. It was supposed to be our chance to finally see the dormant monster at the center of our galaxy wake up and eat.
And then the flyby happened.
And nothing happened. G2 sailed right on by. It got a little stretched, a little distorted, but it remained a compact object. It swung around the center and just kept on going along its orbit. The fireworks show was a total dud.
Which must have been incredibly confusing. How did they explain that?
It was a major puzzle. The leading explanation that emerged was that G2 couldn't be just a gas cloud. It must have a star hidden inside it, a star whose gravity was holding the cloud together against the black hole's tidal forces.
So it's a star wearing a gas cloud coat.
That became the working hypothesis. But the fermionic core model offers a completely different and perhaps simpler explanation. A black hole, a singularity, is a true point mass. The tidal forces right next to a point mass are incredibly extreme. The gravitational gradient, the change in the strength of gravity over a short distance, is unbelievably steep. That's what rips things apart so efficiently.
Okay.
But the dark matter core isn't a point. It's an extended object. It's a ball. A very dense ball, but a ball nonetheless. While the overall gravity is just as strong, the gradient of that gravity is much smoother.
So the tidal forces are gentler. The pull on the near side of the cloud and the far side of the cloud is more similar.
Significantly gentler. The researchers in this paper argue that a simple gas cloud with no star inside it could absolutely survive a close pass by their fermionic core model without being completely shredded.
So the mystery of the invincible gas cloud, G2, is actually, it's a piece of evidence against a singularity and for a distributed extended core.
It is certainly highly consistent with the core hypothesis. It resolves a long-standing observational puzzle in a very neat way.
Okay, the case is getting stronger. But now we have to face the music. We have to look at the photograph, the Event Horizon Telescope collaboration. They used a planet-sized array of radio telescopes to take a picture of Sagittarius A.
The first one of Messier 87's black hole was incredible, but seeing the one in our own galaxy was a landmark moment.
It's that iconic image, the blurry, glowing orange donut with the dark patch in the middle. And the EHT team explicitly called that dark patch the shadow of the black hole. That sounds like pretty definitive proof.
It is, without a doubt, the strongest piece of evidence in favor of the black hole model and the biggest hurdle for any alternative theory to clear.
Let's break down why. That shadow exists, as I understand it, because the event horizon is a one-way membrane. Light can go in, but it can't come out.
Correct. There's a region around the black hole called the photon sphere, where photons can orbit. But any photon that crosses a slightly smaller boundary, the event horizon, is captured forever. So from our perspective, that region appears as a dark silhouette against the bright glowing plasma in the accretion disk behind and around it.
So if your fermionic core doesn't have an event horizon, if it's just a solid or at least a very dense ball of particles, then light shouldn't be captured. It should be able to, I don't know, bounce off it or pass right through it. Since it's dark matter, we shouldn't see a shadow.
That's what your intuition would tell you. You'd expect to maybe see a faint glow or perhaps nothing at all, but not this sharp, dark silhouette.
So how does the new paper explain the picture?
They address this directly, and the answer lies in the mind-bending nature of gravity in general relativity. The dark matter core, remember, is packing 4 million solar masses into a tiny, tiny region. The gravity is so intense that it causes extreme gravitational lensing.
It bends the path of light that passes near it.
It bends it severely. The researchers argue that it bends light so much that it effectively mimics the appearance of a shadow.
How? What's the mechanism?
Think about the light coming from the hot plasma behind the core. As those light rays travel towards us, they pass by the core, and their paths are deflected, bent away from our line of sight. Similarly, light from the plasma in front of the core is also lensed. The net effect is that very few photons from the region directly in front of or behind the core ever reach our telescopes.
So the darkness we see in the EHT image isn't a hole where light goes to die. It's a blind spot, created by the core's gravity acting like a warped lens, shoving the light aside.
That is precisely their argument. The paper cites previous work in radiative transfer simulations done by members of the team. They modeled what a telescope like the EHT would see if it looked at one of these dense cores surrounded by hot plasma. And the result was a central brightness depression.
A central brightness depression. That is a wonderfully scientific way of saying a dark spot in the middle.
It is. And their key finding is that at the current resolution of the Event Horizon Telescope, this brightness depression caused by lensing is visually and statistically indistinguishable from the shadow cast by a true black hole event horizon.
You're kidding. So the picture we all saw, the one that was hailed as proof of the black hole, could be a cosmic optical illusion.
It could be a case of what we might call gravitational mimicry. The dark matter core mimics the gravitational pull of the black hole for orbiting stars, and it mimics the visual appearance of the black hole's shadow.
That is both amazing and incredibly frustrating. So if the S-star orbits match and the photo looks the same, how on earth do you break the tie? Is this just a philosophical debate now? We just pick the theory we find more elegant?
No, absolutely not. Science is not philosophy. We need a definitive, falsifiable test. We need an observation that one model predicts and the other forbids. And thankfully, the very specific physics of a black hole's event horizon provides one. The smoking gun is something called the photon ring.
Okay, is the photon ring different from that big, fuzzy orange ring we see in the EHT image?
It is very different. That big orange ring is mostly just the bulk emission from the hot gas in the accretion disk. The photon ring is a much sharper, much thinner, and much fainter feature that is predicted to lie right at the inner edge of that glow.
What is it made of?
It's made of photons that have performed a cosmic tightrope act. These are light rays that didn't fall into the black hole and didn't escape immediately, but instead got trapped in unstable orbits right at the edge of the photon sphere. They can orbit the black hole 1, 2, 3, or even more times before finally breaking free and flying towards our telescopes.
So light that's literally circling the drain.
A perfect description. General relativity makes a very precise prediction. A true black hole with an event horizon must produce this feature. It's an infinite stack of ever fainter, ever sharper subrings. It's a direct signature of the event horizon itself.
And the dark matter core.
It has no event horizon. It can bend light. It can create a brightness depression. But it cannot trap photons in these specific, infinitely looping orbits. It will not produce that sharp, distinct photon ring structure.
So there it is. That's the test. Find the photon ring.
Find the photon ring.
If it's there, Einstein and the black hole model win. Case closed. If it's missing,
then the dark matter hypothesis is not just a viable alternative. It suddenly becomes the leading explanation for what's at the center of our galaxy.
So, do we have the technology to see this ring? Is it something we can do today?
Not quite yet. The current EHT image is just too blurry. It's like looking at a vinyl record and only being able to see that it's a black circle, but not being able to see the individual grooves. We need higher resolution.
But that's being worked on.
Oh, absolutely. The NEHT, or Next Generation Event Horizon Telescope, is already in development. It will add more telescopes to the array and use higher observing frequencies, which will dramatically increase the sharpness of the images. Its primary goal is to resolve the photon ring of both Sagittarius A and M87.
So it's a waiting game.
It is. But there's another way we might be able to break the tie, and that involves the gravity instrument on the Very Large Telescope in Chile.
Right, gravity is the one that tracks the S-stars so precisely.
With incredible precision. And it's currently undergoing an upgrade to gravity plus times. This will make it even more sensitive. It will be able to see fainter stars, and crucially stars that are even closer to the galactic center than S2.
And how would that help?
Well, the dark matter core has a physical size. The model predicts its radius is about 1/3 of the closest approach of the S2 star. If we could find a star that orbits inside that predicted radius, that would be definitive proof.
Why?
Because if the object is a black hole, you can orbit as close as you want, right up until you hit the event horizon. The gravity outside the event horizon always acts as if it's coming from a point. But if the object is an extended ball of dark matter,
And if you go inside the ball,
the physics completely changes. According to Newton's shell theorem, once you are inside a spherical mass, you are only pulled by the mass that is interior to your position. The gravity from the shell of matter outside of you cancels out.
So the gravitational pull would get weaker as the star dives deeper into the core.
Exactly. Its orbit would completely stop being a Keplerian ellipse. It would start to precess wildly. It would look more like a harmonic oscillator, sort of bouncing back and forth through the center. Finding a star with that kind of non-Keplerian orbit would be the ultimate smoking gun. It would prove the central object is extended and not a point.
This is all leading us to the really big picture, the so what question. Let's play this out. Let's imagine for a moment that Argwells and his team are right. Let's say in 5 or 10 years, NEHT looks for the photon ring and finds nothing. Or Gravity Plus finds a star swimming around inside the core. What does that discovery actually do to our understanding of the universe?
The first and most immediate consequence is that it solves the singularity problem. This is a deep, fundamental headache that has been at the heart of general relativity since Carl Schwarzschild first solved Einstein's equations back in 1916.
A singularity being a point of infinite density and zero volume.
Yes. And in physics, whatever you get an infinity in your equations, it's usually a giant flashing red light telling you that your theory is incomplete, that the math is broken down and doesn't know how to describe what's really happening.
Nature doesn't really do infinities.
Nature abhors them. If the galactic center is a stable dark matter core, it means that the ultimate collapse of matter is halted by a known quantum mechanical principle, the degeneracy pressure of fermions, before it can reach that infinite state. It means the laws of physics as we know them remain valid everywhere in the universe. There are no holes in reality where the rules don't apply.
That's a huge philosophical shift. It also pretty obviously tells us what dark matter is, or at least what it's made of.
It would be the most profound discovery in particle physics in a century. We would know that dark matter is composed of these light, sterile, neutrino-like fermions. We could stop building bigger and bigger xenon tanks to look for WIMPs and pivot our entire experimental strategy towards detecting these key V-scale particles in other ways.
It would connect the unimaginably small scale of subatomic particles with the unimaginably large scale of galactic structure in this incredibly direct way.
It's the ultimate dream of physics. A unified theory.
And what about other galaxies? There's an interesting idea touched on in the research, this concept of an evolutionary track for these objects.
Yes, the idea of a critical mass. The fermionic core model predicts that the core is stable only up to a certain mass limit, just like a white dwarf star is stable up to about 1.4 solar masses, the Chandrasekhar limit.
So as long as the quantum degeneracy pressure is strong enough to fight gravity, it stays a stable core.
Exactly.
But what if it gets too heavy? If it accretes too much gas and stars over time, or if our galaxy merges with another big galaxy?
Then it's possible it could exceed this critical mass for dark matter. At that point, gravity would finally overwhelm the quantum pressure, and then it would undergo a final catastrophic collapse into a true singularity, a true supermassive black hole with an event horizon.
So the universe might be filled with both. Younger galaxies, or more isolated ones like the Milky Way, might still have their original dark matter cores. But older, more massive galaxies, especially ones at the center of huge clusters that have gone through many mergers.
They might have already collapsed their cores into true black holes. The monster in a galaxy like Messier 87, which is over 1,000 times more massive than ours, 6.5 billion solar masses. That could very well be a true collapsed black hole.
So M87 could be a real black hole, while Sagittarius A is still in this stable pre-hole state.
A failed black hole, in a sense, a core that had enough mass to shape a galaxy, but not quite enough to collapse under its own weight.
That almost makes our galaxy feel gentler, less menacing. We have a stable heart, not a bottomless drain.
It definitely changes the narrative. It reframes the galactic center, not as a destructive engine of chaos, but as a gravitational cradle, made of the very same substance that holds our star in its gentle sweeping orbit out here in the suburbs.
Let's go back to that visualization we started with, the spiral arms, the bulge, the central point. When I picture it now, the image is different. The central point, the monster, it's not a separate entity anymore. It's just the sharpest peak of a vast, invisible mountain range.
That's a perfect analogy. Imagine a huge landscape made entirely of invisible sand. The peak is incredibly high and steep. That's the core. But the slopes of that same mountain extend outwards for hundreds of thousands of light years. That's the halo. It's all the same sand. We just happen to live on the gentle lower slopes, orbiting that distant peak.
And all that sand is passing right through us right now without us ever feeling it.
Constantly.
It's a really humbling perspective. We spend all our time looking at the stars because they shine. They're the bright, exciting, look-at-me part of the universe. But this theory is a powerful reminder that the stars are just the sprinkles on the cake. The actual cake, the structure, the substance, the thing that is the galaxy is the dark matter.
The baryonic matter, the stuff we're made of, it's just a tracer. We're like foam on the crest of an ocean wave. The foam shows you where the wave is and how it's moving, but the foam isn't the wave. The dark matter is the ocean.
And for half a century, we've believed that at the very center of that ocean was a mysterious whirlpool leading to nowhere. But maybe it's just the place where the water is deepest and most still.
It's an incredibly compelling thought. And look, whether this specific fermionic model turns out to be exactly right in all its details or not, its real value is that it forces us to challenge our assumptions. It forces us to question the black hole plus WIMP dogma that has dominated cosmology for so long.
It forces us to look at the same data, the S-star orbits, the Gaia curve, the EHT image, with fresh eyes and ask, what else could this be telling us?
That's the entire scientific process in a nutshell. It's the art of revision. The data is the data. S2 is still moving at over 7,000 kilometers per second. The picture is still an orange donut. But the story we tell ourselves to explain that data, that story is always up for revision.
I want to leave you with one last thought to chew on, a final provocative question. If our own galaxy, the one we know best, might have a dark matter core instead of a black hole, what about all the others?
Indeed.
What about Andromeda? What about the hundreds of billions of other galaxies we can see? The distant quasars powered by what we assume are feeding black holes. Are we looking at a universe filled with these bizarre singularities, these points where physics dies? Or are we looking at a universe filled with these dense, silent, stable hearts of dark matter? If we've potentially misidentified the most important object in our own backyard, how many others have we gotten wrong?
We might be seeing these shadows all across the cosmos, and they might all be the result of this extreme gravitational lensing from dense matter rather than light captured by event horizons. It opens the fascinating possibility that true singularities are actually much, much rarer than we currently believe.
A universe with fewer holes in it. I have to say, I kind of like the sound of that.
It's certainly a less terminal thought.
We are absolutely going to be keeping a close eye on the NEHT and the Gravity Plus instrument, and you can be sure that the moment they either find that photon ring or confirm that it's not there, we will be back to talk about it.
I look forward to it. The hunt for the photon ring is truly one of the next great quests in modern astronomy.
Until then, look up at the night sky. And remember, what you're seeing is just the foam. The ocean itself is invisible. Thanks for joining us.
Thank you.